Looks like we're now recording. Yeah, so we'd like to let G be a linear algebraic group over a field. For this talk, I'm going to work with the characteristic of F not 2. And mostly I'll be interested in G of type C and D. So just a quick reminder, type D is the spin group is the simply connected group. The special orthogonal group is, as everyone is familiar with. The adjoint group is projective special orthogonal. And the half-spin group from the title is the other central quotient, because when this is divisible by 4, there's 2 quotients. And also interested in type C, which I'll be using the notation of the symplectic group and the projective symplectic group. All right. So cohomological invariants, as we've seen in some other talks, were introduced by Serre. So a cohomological invariant of G is, or of G with coefficients in it's a module over the Galois group of the separable closure of F over F. So in a Galois module A is a natural transformation from the first Galois cohomology of G into some nth cohomology of the module A. This is sort of the general setup. However, in particular, a lot of recent focus has been on, in particular, certain choices of A. So when people talk about degree 2 invariants, they're usually talking about invariants into H2 with coefficients in Q mod Z. These are sometimes called Brouwer invariants. These were actually talked about in a previous talk here by Alexander Ludrow. Make sure I spell this correctly. And when we talk about degree 3 invariants, we're usually talking about similar things, but now into H3. And we take a tensor product here of Q mod Z. This Q mod Z kind of has a complicated definition depending on the characteristic of F, which Alexander had summarized. Just, I guess, intuitively, you can think of Q mod Z over F set as the set of units such that they're a rooted unity. This is the general idea. And so when we discuss degree 2 invariants or degree 3 invariants, these are what we're talking of. And there's some notation for these. These form groups because you can have an additive structure over here. Define these as the degree 2 invariants or the degree 3 invariants. This one representing that this Q mod Z is alone, and the 2 representing that there's this tensor product here. So the degree 2 invariants, these Brouwer invariants, for simple groups, we have a pretty nice definition, which I know of from the Book of Involutions. It states that if we take the map from the simply connected cover of G down to G, then this group of degree 2 invariants is isomorphic to the characters of the kernel. So just an example, if we look at the degree 2 invariants of the projective symplectic group, these are going to be isomorphic to the characters of mu2, which is just Z mod 2, because the kernel from the symplectic group here is just 1 and minus 1. And we can actually look or describe what these invariants do. So if we're over some field extension E to H2, this, As was mentioned in Alexander's talk, they're called Brouwer invariants because there's this isomorphism here with the Brouwer group of E. So we can think of these as invariants sending isomorphisms of central simple algebras to isomorphism classes or different classes of central simple algebras. H1 of the projective symplectic group categorizes central simple algebras with symplectic involution. So we'll have some of those here. We have two invariants. The zero invariant is just kind of the constant trivial invariant. It sends everything to zero, which is also the class of matrix algebras. I guess this could be a different M here. And the one invariant is kind of a constant invariant. It forgets about the involution and sends this isomorphism class to the Brouwer equivalence class of the algebra. And for other groups, I mean, when you're working with simple groups, these are going to be finite. And so we have similar nice descriptions. The degree 3 invariants are a bit more complicated. And these have been studied by Serre himself. Rost has an invariant named after himself. Merkurjev has done a lot of work. Garibaldi has studied these. Many people. And so in order to understand this group of degree 3 invariants, there's some subgroups that we name for convenience. The first one is we restrict our attention to what's called the normalized invariants. And these are just invariants which send the trivial F torsor or the trivial object in H1 F of G. And I'll just write it as the class of 1, H1 F of G, to 0 in H3. Mod Z2. So we can restrict to these because there's a nice decomposition. All the invariants can just be considered as a normalized invariant plus where it would send the trivial torsor. So we can restrict our attention to these. And within the normalized invariants, there's a group called decomposable invariants. And the idea behind decomposable invariants is that we'd like to use this nice understanding of degree 2 invariants in order to build some understanding of degree 3. So we can look at this group, the decomposable invariants. And the idea here is that we have a Galois cohomology cut product like this. I guess I could, I don't know, I want this to be F. Yeah, I'll use F's. This is a Galois cohomology cut product into H3. And so this is where degree 2 invariants are ending up. And this is where degree 3 invariants are ending up. And in here, we have classes of elements from the field. And so the idea is to take degree 2 invariants, and through this cut product, build up degree 3 invariants. So the actual definition is that delta, which is normalized, is decomposable if there are some xi in here and some degree 2 invariants, which I'll call delta I of G, such that we can just write delta as a sum over I of this cut product. So as a result of this definition, to continue with our projective symplectic example, the invariants of PSP2N, which are decomposable, this group ends up being isomorphic to this. the units in F mod the squares. And we only have to consider these for the following reason. If we scroll back up here to our description of the degree 2 invariants of PSP, algebras which come with a symplectic involution, so this is in the Brouwer group of E, and algebras which come with a symplectic involution will satisfy that the class in the Brouwer group is order 2. So because of this, when we consider the cut product, these field elements we take only need to be order 2, so we end up taking them from here. And the way this ends up looking, because if we try and take a cut product with this trivial invariant, it's just going to erase everything. So there's really only one invariant to choose. And so the element class of X in here acts as follows. So as an invariant, I guess we could even go up to a field extension and you just inject upwards. Takes, again, these are classes of central simple algebras over E with symplectic involution. And it just sends it to X cup, the class of A in the Brouwer group. And this is sort of generally how the decomposable invariants for groups appearing in this talk will look. They kind of just depend on these field elements, and they build things out of cut products like this. So the decomposable invariants we can understand, we can describe them. To get at the rest of the normalized invariants, we would like to literally mod out by the knowledge we have. Doing so leads us to the definition of indecomposable invariants. And these are just defined to be the quotient of the normalized by the decomposable. And just a warning, these are perhaps not natural transformations. It's more of just a quotient that produces some group. You may not have this nice functorial natural transformation behavior anymore, but nevertheless, this is a useful thing to look at. And yeah, as I said, these are called the indecomposable invariants. And so these have some descriptions in certain cases. For instance, the first big one is that if G is simple, simply connected, so for our largest groups, then they don't have any decomposable invariants. So decomposable are 0, which of course then means that the normalized invariants are just isomorphic to the indecomposable invariants. And this is finite and cyclic. Generated by, as I mentioned previously, Rost has an invariant named after himself. So these are finite and cyclic, generated by the Rost invariant. I saw this results in Garibaldi, Merkurjev, and Serre's book on Galois cohomology and cohomological invariants, and also in there, they compute the order of these groups for various different types, various different groups. So there's sort of a robust description in the simply connected case existing there. For other cases, Merkurjev recently, in his paper from 2016, computed a few things. Among the things he computed, the indecomposable invariants for G adjoint of inner type. And for, I think, all or most of the groups for which he computed this, or for the adjoint groups where he computed the indecomposable invariants, he also described the normalized invariants, so everything was described, but those indecomposable computations were there. And now between the two cases, for groups which are not simply connected and not adjoint, there was a paper by Bermudez and Ruozzi in 2013. It was published in 2013, but it used results from Merkurjev's paper in 2016 from a preprint, or there was some time travel involved. And they computed the indecomposable invariants for groups. They were looked at G is SL of n mod something like this, some central subgroup where P to the R is the maximal prime power of P that divides n, but it's a not adjoint and not simply connected group of type A. And they also looked at, as I was interested in, HSpin, a group of type D. So some examples of what these computations were. If we look at the degree 3 invariants, which are indecomposable of PSP, this was computed in Merkurjev's paper, and it ends up looking like this. Most of the time, there's nothing, it's just 0, but if 4 divides n, you get a non-trivial invariant. The computation by Bermudez and Ruozzi produces a slightly more complicated description, but of a similar nature. So the indecomposable invariants of HSpin are of the form like this. There's some cases, either Z mod 2 or Z mod 4. You get Z mod 2 when n is congruent to 2 mod 4, excluding the case of 2. If n is divisible by 4, you get 4 invariants. And this is all for n greater than 1. If it's odd, or if it's 2, there's nothing. And so most of the descriptions of indecomposable invariants look like this. The description for example, the projective orthogonal group looks the same as the one for the projective symplectic group. But these are the two that I'll be using later. And so some computations have been done. However, in Bermudez and Ruozzi's paper, I mentioned how Merkurjev had computed the normalized invariants as well for most of the groups he considered. Bermudez and Ruozzi just focused on the indecomposable invariants, with the exception of one of their corollaries. So yeah, in their paper, corollary 5.2, this was for HSpin 16. They described the degree 3 invariants of HSpin 16, and they described the full normalized invariants as being isomorphic to this direct sum. Let me just scroll down in the notes I'm following along in. This. So they have a full description of the normalized invariants, and what's going on here is that these are the decomposable invariants. And this piece is from right up here. In the case of 16, you get an indecomposable of Z mod 4Z. So this is just, it comes from a splitting of a sequence, actually. Before I write that sequence, this notion of decomposable invariants comes from a diagram like follows. So I described up above the decomposable invariants of the projective symplectic group, but the decomposable invariants of the projective orthogonal group are similar. H2. And if you look at this composition, you find that you get the same description. These invariants here, these degree 2 invariants for PSO, will be isomorphic to F mod its squares. And through this sort of pullback, HSpin has the same decomposable invariance. But this is coming from a splitting of the sequence. So yeah, it comes from a splitting. I had defined the indecomposable invariance as a quotient, which means we can put them into this sequence. Normalized invariance. Decomposable. And so in this case, they constructed, or they found, this is isomorphic to 4Z, and they took the element 1 and found a suitable preimage, and it ended up being an invariant called E3. And this invariant E3, so they used an injection, or maybe not an injection, they used a map from HSpin 16 into E8. This map into E8 I think can be defined just in terms of root systems. This is type D8, this is type E8, and you can embed the Dinkin diagrams and flesh it out into a group map. And so this gives, let's say, implies a pullback between the degree 3 invariance of E8 normalized into the degree 3 invariance of HSpin. And this takes the Rost invariant to this element E3. And this was all constructed by Garibaldi. So they have this non-decomposable invariant of HSpin 16, and they show that it produces the correct splitting. And so that splitting then gives you this direct sum description. Now, I was able to generalize this beyond HSpin 16 to any HSpin, similarly by producing a splitting of this sequence, but obviously not by using E8. In Garibaldi's paper, where he constructed this, he only considered HSpin 16 so that he could use this relationship between E8. But of course, you've run out of exceptional groups. So for your higher HSpins, you need to look at something else. But this generalization is also just a description of direct sums. So the degree 3 invariance of HSpin for any n. I suppose I should say n is greater than 1. The normalized invariants, they end up looking very similar. In any case, the decomposable invariants are in there. So you get all these pieces. And from, as we saw in Bermudez and Ruozzi's description, sometimes the indecomposable invariants are Z mod 2, sometimes they're Z mod 4, and sometimes they're nothing. So this was when n is congruent to 2, but not 2. This is when n is congruent to 0. This is if n is odd or 2. So we have this full description now, this generalization to the normalized invariance of any HSpin. And so I'd like to spend the last parts of this talk describing how I actually found this splitting. And it was by generalizing the technique, or one of the techniques Garibaldi actually used in the paper where he constructed this invariant. Sorry, my cat is waking up. If you can hear me in the mic, I apologize. So I constructed some injections into HSpin. So generalizing a technique of Garibaldi. So what Garibaldi did, in this paper here, since he was interested in HSpin 16, he looked at the following. He took the symplectic group of rank 2 and of rank 8 and looked at this Kronecker product, sending just the matrices that represent these groups to the tensor product as linear maps. This is the Kronecker tensor product. And since the symplectic groups here are simply connected, but the orthogonal group is not, there exists a lifting. So you can lift this and get the following. We're going to map into spin. And this map now, which lifts over this map, you can describe this explicitly using Chevrolet generators. So this is as in Steinberg's lectures on Chevrolet groups. Just briefly, this is a description of the set points of G in terms of some symbols, where alpha comes from the root system of G, and T comes from the field. And then there's a bunch of relations that this has to satisfy, but it gives you some explicit elements to perform computations with, and you can then track those elements and describe where they go. And so once an explicit description of this map is obtained, you can write down how it behaves on its restriction to the tori involved. In particular, you can compute where central elements go. And so what he did was he considered the composition of this map into half-spin. And with this explicit description, actually an explicit description of both of these maps, you can compute the kernel. And the kernel ends up being just the full center of this group. So if you just mod out by this center, what you get is this produces a map from the projective symplectic groups into half-spin. But this, again, he was stopped at half-spin 16 because of connections to E8 here. But this whole Chevrolet generator lifting, looking at kernels thing doesn't depend on 16. You can generalize this. So generalization. You can look at, sorry, not projective, just symplectic. You can look at any symplectic group of 2n with another of 2m. Consider it mapping into the orthogonal group at 4nm. This again will give you a lifting into spin, which you can again compose into half spin. And the center, or the kernel of this will be the full center. And so you can produce these injections for any n and m. And so it's this map which ended up giving me the splitting of that sequence. So let me just catch up in my notes. Yeah, so once this map was obtained, there is a result, which is that if you have a map just between linear algebraic groups from G to H, you get a commutative diagram of degree 3 invariance. Decompose them. So this is just the exact sequence at H. And of course, there's also a copy of this exact sequence at G. Here. and you get maps downwards. These are just the pullbacks of the invariants from H to G, but this diagram will commute. So this diagram commutes. So now, in order to get at just descriptions for half spin, it's just picking N and M cleverly and applying the sequence. So for example, so for half spin, for N, if N is congruent to 2, but not equal to 2, it's something like this, where M is odd. And then we can consider PSP4 cross PSP to M into half spin for N, using these maps above. And what this exact sequence, or what this commutative diagram ends up looking like, on the top, we'll have the objects for half spin. The decomposable invariants look like this, as we've seen. We get the normalized that we're curious about. And in this case, the indecomposable are just Z mod 2. Down here, the normalized invariants of this group. These have no indecomposable invariants in this case, and the decomposable is just the direct sum of the two decomposable invariants for the symplectic groups. This map is just the, I guess it's the diagonal embedding. It sends some class to the same class twice. And what you can end up showing is that if you have some invariant here and you look at 2 times this invariant, it has to have been decomposable and it has to map to 0 through this injection. And so 2 times that invariant had to be 0, and so it had to sit over the class representing 1. And so you get a splitting. So I guess it's just if delta maps to 1, then you can show that 2 delta maps to 0, but it also does so along an injection. So it has to be 0. So you can take the map backwards, produces a splitting. So this, sorry, there should be zeros here. I guess it's not super important. So you get a splitting in this case. And in the other case, it's similar. You'll get Z mod 4Z there instead of Z mod 2, and there's some different cases here. But the idea is that just by exploiting the fact that this part of the diagram is an injection, we can show that these sort of just naive choices, any choice of a pre-image of 1 will produce a splitting. And then once the sequence for half spin splits, this just follows immediately from the knowledge of the decomposable invariants and the computations of Bermudez and Ruozzi. So we have a description of the normalized invariants. And in one case, we can actually explicitly describe all the normalized invariants. So an explicit invariant when N is congruent to 2 mod 4. So this also comes from Merkurjev's paper. So we're going to consider half spin for N into the projective special orthogonal group. And so in figure 16, Merkurjev constructs an invariant, he calls it I, and it's a degree 3 invariant of PSO. And it's a degree 3 invariant, which represents 1. So it's a non-decomposable degree 3 normalized invariant. This is, in this case, this. And just to briefly outline how this invariant works, there's degree 2. So we're going from the first Galois cohomology of PSO via I into here. The Brow group. And as Merkurjev notes, this cohomology set is isomorphism classes of a central simple algebra A with an orthogonal involution and an idempotent element, idempotent in the center of the Clifford algebra. And this PSO has maps in from special orthogonal group and maps in from HSpin. This gets mapped to from some pair AX here. A is in the algebra, fixed by the involution, and X is an element of the field, so that X squared is the norm of A. Anyway, there's just some pair here that gets mapped down to this class of algebra, and I takes this information and maps this to X cup A. So it's also defined in terms of cut products, but because this X depends on the algebra A and isn't fixed, it's not decomposable, it just sort of looks like one. And so the pullback to HSpin just takes some element Y here, maps it to some such A, and through this process we get this description of this invariant. Now, I restrict it to the case when n is congruent to 2. This works for any n, actually. But in the case when n is congruent to 2, if we look at the groups of indecomposable invariants, decomposable, which this we know is Z mod 2, there's a pullback just from the projected, or from the normal surjection. Because these are split groups, this map between the indecomposable invariants, this is described by Ross multipliers. So you can just compute what the Ross multipliers of this map are. And what ends up happening is that this is isomorphic to Z mod 2 as well. And this is just an isomorphism. So this pullback to HSpin, since I represented 1 in this group, it represents 1 in this group. And so it actually gives us the non-decomposable or a non-decomposable normalized invariant. So if we scroll way back up to this description of HSpin, the pullback I will describe the non-trivial invariant here. We also know the normalized invariants, sorry, the decomposable invariants. So we have an explicit description of all the normalized invariants. You can also construct I and look at the pullback in the case when n is congruent to 4. Or sorry, congruent to 0 mod 4. So if n is congruent to 0 mod 4, can still pull back I. However, in this case, if we take this picture, this group is, it's not wanting to let me pick my eraser. All right, here we go. This group over here changes. Why can't I select my pen again? Sorry, everyone. That's fine. All right, here. This ends up being Z1 4Z. And the Ross multiplier also changes, so this is not an isomorphism anymore. This is represented by ×2. So the one element here gets sent to the two element there. So the pullback of I describes half, I guess you could consider. I mean, the element representing 0, we know it's just the decomposable invariance. And then the decomposable invariance with this pullback gives us the elements over 2. So we have half of them, but I'm not sure of an explicit description for the elements over 1 or over 3. So yeah, not sure in that case. But still pretty good when it's congruent to 2. We have a full description. I guess I have a few more minutes. One note, this restriction, so at the beginning, we assumed that the characteristic of f is not equal to 2. For most of this, for the Chevalier description for groups of type D and all of these invariants and stuff, I don't think this actually matters, and it could be removed. There were some additional things I was looking at. I was working with spin of type B as well, where I think there might be issues, but for most of this, I think you can remove it. However, this part about Merkurjev's invariant, and so Merkurjev constructs when the characteristic of f is not 2. So if the assumption of what the characteristic is removed, then this pullback or this invariant no longer is around for us to pull back. So again, then I have no explicit descriptions of these invariants. Yeah, I guess that's my story about HSpin. Thank you.
Okay. Thank you very much. Thank you very much. Let's thank a speaker. So, is there any question? Any question? Any question?
So for spin 16, how do you get around E8? You have some way of constructing this element that comes from the Rost invariant E8.
Yeah.
Without actually using E8. So I didn't quite catch how you do that.
So the element coming from the Rost invariant is just a pullback once you have the injection, but the injection is sort of defined in terms of, so spin 16 is type D8. So something like this. It's 3, 4, 7, 8. And then you have a group of type E8. 4, 5, 6, 7, 8. And so this was what Garibaldi did. And what he did was look at, there's a longest root over here. I guess I should make a dotted line. And he took this as the root system of type D8 to form an injection. And then based on co-roots, and you can describe this map just explicitly in terms of the Chevalier generators sending. So the Chevalier generators have these X alpha elements, but in terms of these, you can define H alpha elements, which are your central torus elements. Those are corresponding to roots. So if you had some like H alpha here, it would get mapped to the corresponding, it's 3 away, H alpha here. And you get an injection this way, or maybe not an injection, but you get a map this way. And so once you've defined, so this gives, you can look at the center. And once you do so, I think when you just quotient out by the center, you get HSpin. And then it's just pulling back the Rost invariant via, via the map on invariance. Sorry, normalized into HSpin. This should be HSpin. But I think most of the work here was by noticing this root system embedding.
So do you have some way of constructing this same invariant without using E8?
So it's just something. Sorry, what do you mean by the same invariant without E8? Just some representative of a non-decomposable invariant in HSpin? Yeah, I mean, I guess using Merkurjev's invariant I is the same idea, but in cases where that I isn't there, I'm not sure, like for HSpin for n, I don't know what to put here. If that I for PSO isn't around, I haven't spent enough time thinking about it, no.
Okay, thank you.
Questions? More questions? So I have a small question. So about this. So you have this Kronecker map, right?
Mhm.
I mean, used by Garibaldi, but there is one also for twisted groups, right?
Yeah.
So did
Yeah.
you try to think about maybe you can get some computations for twisted groups? Or?
Yeah, so I wasn't actually focusing on twisted groups too much because Bermudez and Ruozzi did their computations for split HSpin and split SL and such, so I was working in that case. But I believe I mentioned that Merkurjev's computations were for adjoint groups of inner type. So for the non-split groups, he has all those computations, and there is some promise there. These maps, for instance, like this one, HSpin, of course, these give you maps over the separable closure. Which is kind of a pain to write out. But anyway, you get these maps over the separable closure. And you can use Galois descent here, find some appropriate element relating to, if you have, I guess I'll just write them in, but if you have some algebra 1 with some symplectic involution, you can use Galois descent. There's some appropriate cocycle, and these maps actually end up being Galois invariant. They respect all the different Galois actions. So Galois descent works on both sides, and you get something like this. I guess you don't need the two n's anymore. A will be of degree 2n, ESPA2 into some HSpin A sigma. And this A will be A1 tensor A2, and the sigma will be psi1 tensor sigma. So I guess I should have just wrote that in there. But yeah, this construction with Chevrolet generators works in the non-split case. You just have to use descent. So these maps are around in the non-split case. I just didn't have access to or couldn't find computations of the indecomposable invariants for non-split HSpins, so I couldn't use the same techniques, but that's kind of a next goal is in these other cases, finding the computations of the indecomposable invariants and doing the same thing.
Okay, yeah, thank you. Is there more questions? More questions? Okay, if not, then let's thank a speaker.